I'm Jim Handy. Tom Coughlin was supposed to be presenting alongside of me. He's not going to be able to be here today, so I am going to be presenting alone. But hopefully that'll work out well for you. But anyway, this is mostly spawned by a report that the two of us have written called. It's an emerging memory report that's by both Objective Analysis, my company, and Coughlin Associates, Tom Coughlin. So I'll be talking about that a good bit. We're going to be talking about AI, which seems to be the big success story for chiplets, mostly because of high bandwidth memory, which is used in there, and also because of the chiplets that are used in multiple die GPUs. We'll talk about new memories and how those fit in with chiplets, because new memories actually mesh very well with it. And then talk about how that affects energy and how it will boost cost performance. So first, I'll talk about AI and chiplets. What is a chiplet? For those of you who are not semiconductor people, I've been in the semiconductor industry for almost my entire career, and so I live, eat, and breathe this stuff. But a chip, one of the big problems with making a semiconductor chip is the optical equipment that's used to produce the chip. You end up photographically producing the chip, and there's a limit to the size of a die that you can make using today's equipment. And that's called the reticle limit. And because of the fact that people wanted to build larger devices than what the chip would do, then they ended up breaking the chip design down into what are called chiplets, and they'll actually make two different devices and tie them together and try to make it act as much like one chip as they possibly can. It moves us past certain limitations of Moore's law. It's not that they're really limitations of Moore's law, it's more that they're limitations to the optics used to produce the chips. And Moore said in actually his second paper, he said, what are the things that allow this Moore's law phenomenon to happen? This was like in 1975. And he he attributed it to three things. One was that the transistors get smaller. And everybody's always assuming that that's all there is to Moore's law. But he also said that the die size gets bigger. And that was something that took a lot of engineering to do. The chip size gets larger. And that's the thing that's limited today. And then he talked about cleverness. And this is just things about how do you get more functionality onto a chip without necessarily changing anything else about the transistors or that kind of stuff. And some of that is architectural. Some of that is going into the third dimension, which 3D NAND has done. And there are a lot of other ways that this has gone. And cleverness is actually what fuels the chiplet revolution here. But the big deal is that the largest chip that lithography equipment can make today is 850 square millimeters. And that's a really big chip. Most DRAM and NAND flash chips are somewhere between 100 and 140 square millimeters. But that's called the reticle limit. Ideally, the data would never leave the chip, because we'll see in a little bit when I talk about capacitance and driving capacitance out of a processor chip that there's a real problem when you go off chip, because all of a sudden everything loads down the signals with capacitance. And so you're trying to stay on the chip as much as possible. It gives you faster data communication. It gives you lower power consumption because you're not charging and discharging capacitors all the time. And chiplets allow this to happen on a larger scale than before, because the connections between two chips inside the same package have extremely low capacitance. They're already widely used. I've got a bunch of pictures of different devices here that use chiplets. You always have some product in a package that is made out of these little chiplets. So the chiplet is the little pieces of silicon inside the larger package. If you look at all of these, this one in the center, the vertex, is probably the easiest one to make out that way. You can see that there are actually, of the larger part up there, there are actually 4 long, skinny bands. They kind of look like floorboards that are there. Those are actually parts of an FPGA that are all connected together with thousands of connections on those long sides of the devices there. And then finally, you've got 2 HBM chips. This is high bandwidth memory. And that's DRAM that is connected down at the bottom. So these are all chips that are in mass production that use a chiplet architecture. Hyperscalers are driving most of this. It's mostly because hyperscalers have enormously deep pockets. They seem to be able to spend billions of dollars on things. And this is 6 companies. I like to say it's 5 A's and an M, because it's Amazon, Azure, Alibaba, Apple, who have I left out here? Alphabet, and Meta. This is all of those companies from their financial reporting that they do every quarter with their earnings statements and how much money they are spending on capital spending for their data centers. And you can see that up here at the very most recent quarter, they've gotten up to about $100 billion, that's billion with a B, in capital spending for these data centers. They're spending a ton of money on these things. And the reason why they're buying the next generation of GPUs or cranking out their own GPUs or TPUs or XPUs is that they find that they can actually, with the newer processor, cut their costs because of the fact that a newer processor outperforms the older processors by more than double. And it usually lowers the data center energy use, which is a huge deal for these companies. If you take that same curve, which is now the red line up here, and you compare it to NVIDIA's growth, you know, NVIDIA is the darling of Wall Street right now because it's just been growing like crazy. And this is just the data center side. There are 4 businesses at NVIDIA. And up until about 2022, the data center was smaller than the gaming business. That turned around. The gaming business has just been, if I drew it on here, it would be a straight line down there around, you know, $2 billion or so. And the data center business has gone crazy up here. So that shows, though, that NVIDIA is doing very well. But what's also interesting about this is that the data center spending is growing faster than NVIDIA is. This is because NVIDIA is under constraint, that nobody sets up their company saying, we're going to grow at this kind of a rate. And so because of that, they've been capacity constrained. And they're shipping as much as they know how, but, you know, and as much as their suppliers can give them. But they can't ship that much. And so, you know, this is something that looks like it's going to last for a while. But the thing that seems to be working, you know, in a strange way with this is that if you take that capital spending and you say, okay, these companies' revenue must be growing at the same rate of capital spending, and that's a healthy relationship. So you know, I took those numbers and I said, okay, we've got the revenues for all these companies, we've got the capital spending. How are they doing from the standpoint of capital spending as a proportion, as a percentage of their revenues? And it's gone up. They used to be very level, about 12 to 15% of their revenues would be spent on expanding their data centers. And now they've zoomed up to 25%. That's probably an unhealthy situation. So there is a possibility that we're going to have some kind of an economic thing slowing down the growth in this area. But for right now, it doesn't look like anybody's going to stop. Now, the effect that this has had on high bandwidth memory, which is a kind of a chiplet, is that the DDR DRAM business was moving along at a kind of a low growth rate before. You've got that dip over there in 2023 because we had a really bad 2023. But in the meantime, HBM became important, and it's growing far faster than DDR. So the companies that make DRAM, which are mostly Samsung, SK Hynix, and Micron, are doing extremely well off of this by shipping HBM. Let me just take a second. I didn't put in a slide about what HBM is, but HBM is you take a DRAM chip that has what are called TSVs. These are wires that go through the chip that allow it to connect to something underneath it. And you put it on top of another DRAM chip that also has wires that go through the chip. And you do that, today they're doing it 12 times. So you have these 12 high HBM things where there are 12 DRAM chips on top of a logic chip. And so those little squares that I was showing you in those photographs of the different devices when I was talking about chiplets, those squares were stacks of anywhere from 2 to 12 DRAM chips on top of each other. It gets you phenomenal speed to go only the distance of the thickness of the chip down through. Not only that, but they also thin the chips so they don't stack up too high. And so you get this great speed because you've got incredibly short wire lengths. You've got thousands of connections instead of the tens of connections that you have in a normal ball grid array that a DRAM is packaged in. And you end up presenting the data to the processor 1,000 bits at a time. Soon, with what's called HBM4, a new standard, you're going to have 2,000 bits at a time of data going into the processor. So you're getting phenomenal bandwidth. The DRAM's latency is still about the same as it was before, but it gets you a lot of speed. But this is allowing the GPUs to process very quickly. And so because of that, then this market is, well, first of all, because of that, then HBM is very popular with GPUs, and the market is really taking off. So I'm coming up with a report on this, and I stuck this slide in there so anybody looking at the slides that are online can have a look. We're coming up with a report soon on HBM. Chiplets enable new memory types. And this is something that ties into what I talked about before, that Tom Coughlin and I have been working on a report for the past 8 years, I think it is, on new memory types. And these are memories that are not today widely accepted, but they are likely to take a bigger role in future computing technologies. And so today's chiplets are really only for ultra high-end applications like the HBM that I talked about. And the packages that these go into, all of those things that I showed the photographs of in that earlier slide, are $10,000 to $50,000 devices. Chiplets tend to be used to make up for the fact that you had this Moore's Law problem and you needed to get a very large die size. And you put two Blackwell GPUs together. You know, they're 814 square millimeters each. And so that gives you, just this colossal size GPU. You take that 814 square millimeters, you take 96 DRAM chips because you've got 8 HBM stacks around it, and each of those 8 HBM stacks has 12 high DRAMs in them. That's another 120 millimeters, square millimeters each for those chips. And then you've got HBM-based logic chips. That's the last chip on the bottom of the HBM that I was talking about. That's 120 square millimeters as well. And it gives you a total silicon area of about 20% of an entire silicon wafer. So basically, it takes a full silicon wafer to make 5 or so GPU complexes on the order of the Blackwell. It's just an amazing consumer of silicon. But they're basically two processes that are very different from each other. When you're making silicon, you put it through thousands of steps, and those steps end up being very different for DRAM than they are for logic. DRAM is optimized to be able to get very cheap capacitors, which is where the storage is. It's inside capacitors. And with logic, you want to have extraordinarily fast transistors. And those two processes are very different from each other. And so because of using the chiplet approach, they can take these two processes and put them together into a same package and act as if they have two processes working together. If you tried putting those two processes together on a single silicon wafer, it would end up being extremely expensive and probably wouldn't give you an awful lot of product. So in the future, what we're expecting to see is more chiplets will go into more applications. Right now, it's for $10,000 plus chips. It's going to go down to smaller die sizes and cheaper type applications. But also, we're expecting to see more than just the logic and DRAM that we see today. We're expecting to see NAND flash go in there. As a matter of fact, SanDisk, one of the first things that they talked about when they spun out of Western Digital was that they were going to make high bandwidth flash. They said, NAND flash has always been optimized for cost, nothing else. And we're going to design chips that instead are optimized for speed and bandwidth. We're going to take that, 2048 bits of I/O and feed that, completely in parallel. So we're going to have something that's very high bandwidth read. However, high bandwidth flash is limited by certain physical properties to be able to write very quickly at all. And so we're not going to see fast writing on high bandwidth flash. And what that means is that it's probably going to be going more into inference applications than into, or well, it's probably not going to be used at all in training applications because training is a very high write type of an application. We're also seeing an awful lot of interest from the people who put together optical modules on doing optical interconnect. The type of semiconductor used for optical interconnect has nothing to do with silicon. It's all gallium arsenide, gallium and indium arsenide, different things like that. And so we're going to see, as adoption of more and more optical interconnect kicks in, we're going to see chiplets that bring optical interconnect inside the package rather than using electrical interfaces on these. We're going to see these memory types that we haven't seen an awful lot of before. And that's MRAM, which is a magnetic RAM, resistive RAM, ferroelectric RAM, which is, that's a different beast that's been around for really actually quite some time. It was actually the first non-volatile memory in existence in 1952. And then phase change memory. And we'll also see true heterogeneous integration. That we'll see a single package that has not just DRAM and logic inside, but it will have DRAM, logic, optics, some type of emerging memory technology, probably a power chip, because people are starting to talk about putting power chips inside the package. You know, there's the power control, voltage regulators, and that kind of stuff. But it will also go into these lower cost products. Something that I've used as a demonstration before in a presentation is this little tiny LED that flashes in different colors inside a single LED package. It ended up that it took 3 different wafer technologies to be able to make that happen. A logic one to flash the colors, and then 2 LEDs that had 2 different colors that were made out of different things, and that's how the different colors came about. So we'll probably see more places where people say, hey, we can do heterogeneous integration and have, LEDs and logic in the same package. We'll also see more stacking as that technology develops. I didn't say that. I'll be taking questions at the end, too, if I don't gab too much and use up all the time. So this is like a far-off look from an IEEE article about how a processor may end up looking in the future. And so you've got, and these are things that people have been experimenting with in the past. You've got high-density, non-volatile memories, and this is those exotic memory technologies that I was talking about, the MRAM, resistive RAM, ferroelectric RAM. And then you'll have some logic underneath made out of energy-efficient FETs. And this orange layer right smack in the middle, that's a thermal thing. That's to get rid of the heat dissipation that's in there, because heat is already a big issue. But it's going to become a bigger issue the more things that are stacked in there. And then you'll maybe see computation and memory inside of these. It's not something I'm not going to touch on, but it's something that I need to put together a report on in the future, because a lot of people are talking about that now. It's where you actually make a memory chip that's got computing elements inside of it. And then, finally, on the bottom, you've got more heat removal. Talking about those new memory chips, those memories are made in processes that don't mix well with the logic process. It's an awful lot like what I was saying about DRAM and putting DRAM in a logic process. They just don't like each other. And some of these new memories use elements that contaminate silicon fabs. And so a lot of the people who make silicon chips really don't want to have them in there. Ferroelectrics are like that. One of them uses strontium, another one uses lead, and both of those are highly contaminant of silicon processes, and so they have to be managed extraordinarily carefully, and they could bring the whole production line down if they're not managed right. But also, established memory and logic processes disagree. Memories make logic slower. Logic makes memory more costly. Neither one of those is a good thing. And so if you have, mixed memory and logic, then you end up with a slow, costly chip. Nobody wants that. So, what you can do is break those apart into chiplets, and you get more flexibility. But also, you have the ability to put any size memory with your logic chip, or you can put multiple logic chips with a certain memory so that they can share the memory, and as in pooling, like CXL allows you. And it also allows you to scale your options that you sell, just like a cell phone. If you buy a cell phone with a 256 gigabyte or a 512 gigabyte or a 1 terabyte memory inside of it, that's just a matter of how many NAND flash chips they put inside. And you'll see that in the future with processor chips where they say, you know, how big of a cache do you want inside the processor chip? How much HBM do you want? Sure, we've got this model that's got that. Now, there's a problem, too, that is forcing the industry to look really hard at emerging memory technologies. This is a little bit of a backwards graph, because what it's showing is the process technologies running across here with the smallest one on the bottom. And the smallest one is towards me, and the largest one is, you know, on the far side. The reason I put it together that way is because that's the way the time goes. The 30 nanometer process is the oldest process, the 5 nanometer and smaller processes are the newer processes. And so it kind of looks like a time scale. And what this shows us is that over time, the size of 1 bit of SRAM has gone down steadily with the processes, and then all of a sudden it started to level off. And this is having a really bad effect on processor chips, because a typical processor chip has an awful lot of SRAM on it. This is a typical SRAM chip. It's some old Intel processor from about, I don't know, 8 or 10 years ago. But what you see here is the top part, which is kind of random, is logic, and the bottom part, which is a very regular kind of a structure, is the SRAM. Now, what happens with that scaling that I showed you in the last chart is that as you go scaling further down, then the SRAM becomes a bigger and bigger part of that overall chip. This is just some junk that I messed around with Photoshop. And you end up with this chip that's almost all SRAM, and it really should have shrunk down to a much larger size, a much smaller size. This chip here in the corner has got the same proportions in it as that big one off to the far end of the slide, but it's just everything has been shrunk together, the SRAM and the logic. That's what everybody would like to happen. They want to get the cost down, and you get the cost down by making the chip smaller. And you can't make the chip smaller if the SRAM is sitting there not shrinking on you. And so what do? Well, the answer is to use an emerging memory technology or a new memory technology to do that, because all of these memory technologies promise to shrink a whole lot smaller than SRAM. But also, SRAM uses 6 transistors per bit. And most of these technologies use 1 transistor per bit. Some of them use 2. But either way, it's going to be a smaller memory cell than the SRAM cell. I say that, but there are certain other issues that might get in the way, and they have for MRAM, and so that's why we're not already there yet. Something nice is that SNIA put together something with Intel's Optane in mind, which is the non-volatile memory programming model. And that has that is structured in such a way that it's supposed to support non-volatile memory anywhere that it appears in the system. And so if you put a non-volatile cache into the processor, then you ought to be able to use this non-volatile memory programming model to take advantage of that non-volatile cache. I'm stumbling over my saying that. But yeah, the idea here is that you don't have to make your persistent writes out to Optane memory, which was one of the big selling points for Intel, or out to the SSD, which is an incredibly slow medium compared to a cache memory. But instead, if you can persist things to cache memory, you can come out of a sleep state or restore operation from a power failure just considerably faster than you can in today's systems. So that's going to be a big plus. And this is just another ad for a report. I've got cute little cards that I can hand out to people afterwards. If you want to buy a report from us, we talk about it in that. That's going to stay in the slides, so if you download the slides, then that'll be in there. So next I wanted to talk about energy. That's the third thing on the agenda. Okay, so this is way too complicated of a slide, and I'm sorry about that. First of all, ignore everything below the chart, because all that does is that just tells you where the data came from. But what I want you to notice is on this chart is that you've got what the energy consumption is for DRAM, and this is from an academic paper. You can see the kind of turquoise color is the DRAM actually doing the work that you ask it to do, but also DRAM bits tend to droop over time. And you need to kick them back up or kick them back down to the ones or zeros where they're supposed to be. And that's called a refresh. And when you're refreshing it, then that's just wasted power. But it saves you a bunch of money because you get these little tiny bits, and the DRAM is cheaper as a result of that. So that's why it's called dynamic. They could have probably given it a more appropriate name for what it's doing, but dynamic sounded a whole lot better. And that's where the DRAM name came from. Now, one of the things about DRAM refresh is that it changes with the size of the memory array, but it also changes with the temperature at which you run the memory. Because if you run the memory hot, which happens in an awful lot of data centers' servers, then you end up having to refresh it more frequently because that droop happens faster. And so you've got room temperature over here on the left. 64 milliseconds is the average refresh time at room temperature. But if you take it up to an extended temperature range, then you have to double that refresh rate. And that ends up, if you look at that 16 gigabyte on the very far right-hand side of this, then you'll notice that it's about 50% refresh and 50% actual power doing things that you want it to do. So DRAM requires more refreshing when it's hot. On the chart, it's showing 15 to 55% of DRAM power goes to refresh. And then, according to the second source down here, DRAM accounts to up to 46% of the power in a server. That's a lot of the power in the server. So if you've got that going on there, then that means that basically in a 100 megawatt data center, you're going to be burning 25 megawatts just on DRAM refresh. It would be great if you could get rid of the DRAM as a result of that, or to fix that. And this kind of shows how that's a vicious cycle. That if you've got more heat up here in the 2 o'clock position, then it causes leakage. That leakage loses bits, so you need to increase the refresh frequency. And the refresh power increases when you do that, and that power generates heat, and the heat causes more leakage. So it just keeps going in a kind of an endless loop with that. It would be great to get away from that. And then there's another culprit to energy that's a big deal, and that is that moving the power around. I forgot to say that this is actually a slide that I borrowed from another SNIA presentation. This is from the 2017 Persistent Memory Summit, and it's something that was shown by Steve Pawlowski. Brilliant guy who I think is still a fellow at Micron. He was a fellow at Intel before that. But he said, a floating point calculation is 17 picojoules. Moving data from DRAM to the CPU takes about 17,000 picojoules, or 1,000 times as much. And if you look at that 1,000 to 1, that means something when you look just at the math numbers. But then when you look at money and you say, what's 1,000 times a dime? It's a $100 bill. And all of a sudden it's like, oh, yeah, that's pretty darn important, isn't it? So, how do you get rid of moving that data, or, the energy of moving that data? And part of it is getting rid of the capacitance, which I talked about before with HBM, between the processor and the DRAM. And I like to say that the processor sees everything as a capacitor. The processor's in a socket, and that socket looks like a capacitor. And there are other sockets in there for the 3 DRAM DIMMs that I put in here. So each one of those sockets looks like a capacitor. But also, the PC board signal traces down at the bottom look like a capacitor. And then all of the signal pins inside the DRAM modules look like capacitors. But then finally, all of the DRAMs look like capacitors. And so you've got basically tons of capacitance hanging off of the processor. And the ideal would be to get past that. And using chiplets, using HBM, can get you past that. It lowers the amount of power that you burn moving data back and forth between things. It doesn't change the refresh power problem, but it does change the moving the data around. And then looking at flash, that also uses a lot of energy. You've got basically the structure of flash, and a lot of you already know this because a lot of you are very close to the innards of SSDs. But inside of flash, you've got these various blocks. And each one of these blocks is made up of pages. And a page gets loaded with bits, and that takes, about 79,000 picojoules. This is just like one old data sheet that I looked at for this. You move that over into the block, and then fill up the block with pages, and that ends up taking you about 263,000 picojoules. So, this is getting pretty big compared to that 17,000 picojoules that I was talking about before. And then you multiply that by, and then you erase the block. You have to erase it all at the same time. And that ends up taking about, 2 million picojoules. And you say, okay, that's an awful lot of energy. But then you divide it by the number of bits in the block, and it ends up being about 6 picojoules per bit every time you program it. But you do have write amplification, where because of the fact that it's got this block structure, and you have to erase a block, and you have to program it in pages, and some pages get invalidated, and then they have to get moved to another block, and all of that, that ends up giving you write amplification, which if you've just got 2 times write amplification, then that'll take you up to 12 picojoules. I've heard that typically 4 times write amplification is a more normal number for inside an SSD, and so that'd take you up to 24 picojoules. And so I'm saying all of this so you can compare it to the emerging memories that we detail in our report. So this is a complicated table for our report. I only want you to look at a couple of lines in here. One is the types of memories that we looked at in this particular table, and the other is what is the write energy for each one of those things. And that's small print, so I put it down here on the right-hand side, the write energy per byte for all of these things. And that's per bit down there in the thing on the table, so this is per byte. So these are all numbers that are 8 times as large. And you look at those and you say, okay, we were just talking about, I think it was, what was it now on the last slide? I'm just going to back up a second. Okay, 6. So 6 picojoules here, and we'd be going to, let's say, 24 picojoules per bit written on there. And you compare that to each one of these things, and 24 looks better than this 80 picojoules here. It looks a whole lot better than the XRAM 1200 picojoules. So let's just say, we're not going to use those. But still, you've got a couple of different MRAMs that are, pretty good on the picojoules per bit. You've got FRAM, which is really good on the picojoules per bit. And then Weebit's got a resistive RAM that's 8 picojoules per bit. All of those offer a whole lot better of a solution for writes than NAND flash. And so we believe that these new emerging memory technologies will find a place in persistent memory in computing, and probably in chiplets, partly because of that. And that is helped an awful lot by the fact that you've got write in place, and so you don't have write amplification with these devices. So there are a lot of approaches that are under investigation. You've got replacing DRAM with a new memory technology, and that would be one of those ones that we had on the list. Intel's Optane proved that to be very difficult from an economic standpoint, because it costs a lot of money to bring a new memory technology in. But SanDisk plans to do this again. SanDisk is really doing an awful lot of new things, high bandwidth flash, and reviving this persistent memory. So we'll see what happens over time. Another approach is to move memory into the processor. And that's already been done, really, because you look at caches, and that's what it is. But the big difference is whether or not you do more than just have logic and a cache, but instead you pepper them all together into SRAM bits that are right next to logic bits. And that can help an awful lot, but it also makes the architecture very application specific. But HBM is actually a small step in that direction. Moving the processor into memory, it's another way of looking at the same thing, but there are some people who are putting neural networks, analog neural networks, into these new memory technologies. So, new memories are actually very good for analog neural networks. So we'll probably see some of those applications in edge applications or endpoints. And, once again, support for persistence in memory and cache, and that's going to be a big deal. And then finally, let's look at cost performance. And I don't know how I'm doing time-wise here. Oh, not bad. Total cost of ownership is the capital expense. How much did you pay for the computer? And then the operating cost, which in modern hyperscale data centers, that's almost exclusively energy cost the operations don't really require an awful lot of human intervention, and there isn't an awful lot of repair. So, maintenance, that kind of stuff. Energy is a very large part of the equation. And so you want to remove the need for DRAM refresh. You want to reduce the data transfer costs. This is the capacitance between these things. You want to reduce the high write energy that you have in NAND flash. And you want to reduce the number of times that you move the data to storage. And that you do by incorporating more memory into the processor, which you can do with chiplets. And then capital expense follows the die cost because new memories, that basically means that if the chips are cheap, then the system will be cheaper. And so you can use new memories to improve the chip scaling and get those costs down. So we think chiplets can bring new memories into the package, and that's probably going to be happening out in the long term. And it's just something for you to think about right now. It's certainly not something for you to act on today. So, an important part of all of this is standards. And, you might have heard about some of these standards. HBM is one of them, and this is an NVIDIA GPU, and those are the HBMs. It's just, if you look for the small square thing, that's the HBM. The reason why they just look like they're silver is because you're looking at the back of a DRAM die. And that's just like the back of a piece of silicon. It's got no processing on it, and so it doesn't look like much of anything. These are pictures of both the front and the back of marketing, beauty samples of HBMs from the leading DRAM vendors. SK Hynix is actually the leading DRAM vendor right now simply because of their having HBM that Samsung didn't have. And they beat Samsung to market, and since 1993, I think Samsung was #1 in the DRAM market. All of a sudden, this past year, SK Hynix has become the leading DRAM manufacturer. And Micron is also playing an important part. Samsung's selling HBM2 products, which are a little bit older, but they're still doing a very good job in that. The golden side on all of these is the business end of it. That's where all the connections are. And I once looked at the connection diagram for one of these things, what each one of those pins were, and I told you there are 1,000 data connections. That's only a part of the story. I think there must be something like 5 times as many connections on these things as just the data connections, because you've also got address pins, control pins, you've got power pins, and probably just tons of them, because the way that you get rid of noise problems in transferring data is by adding more power pins. And so, that it kind of looks like just gold, but it's a lot of pins. But the big deal is that because of the fact that there are 3 sources for this, you've got competitive costs. These people are competing against each other on cost as well as quality. And so that is also going to happen with other kinds of chiplets. And we'll see UCIe, which is a standard for connecting chiplets together, as being a good tool for this, because this is a standardized interface. Right now, most of those packages that I showed you in the very early slide that had the photographs of all of those chips, most of those use proprietary interconnects between everything except for the HBM. So UCIe is trying to be a standard that will be used by the entire industry. And what that means is that if you've got one company's, let's say, optical interconnect chip that uses a UCIe interface, and they've got a competitor that uses a UCIe interface, and you've decided that you don't really want to do business with this company anymore, you just pick up where you left off with the other company. So it's, that's why it's really good to have an open standard, is that will keep there from being supply chain disruptions. It will keep the prices down. So it's kind of like a CXL from a technology standpoint connection inside the package. It uses an awful lot of the CXL protocol. It allows for very flexible data movement, hides differences in memory types. This is if you're using MRAM or ferroelectric RAM or whatever, you can just plop it in there, and the software will take care of any of the differences. And if any of you have to program that, I'm sorry. And then it allows the commoditization of the chiplets. It allows the prices to get down. It also helps reduce costs. That you can make your logic in a logic-only process, which is what they're doing right now with GPUs. You can make your memory in a memory-only process, which is what HBM does. But now you can do it with all of these other memory types too. You can do optics on an optical process. And because of that, you'll have broadly used commodity parts. It's, the 5 different companies that are making 5 different processors that are all optically interconnected are going to be buying the same optical interconnect chips from the same pool of vendors for that. That means those vendors have a much larger market, and larger markets drive the cost down. So in summary, chiplets are going to be moving systems from being large and expensive, or chiplets are going to move from large and expensive systems to small and cheap systems. We see that happening in the future. I've just got the 10-minute warning. New memories will reduce energy by, no refresh, by, having easier write mechanisms, that kind of stuff. And they'll extend chip scaling, so they'll allow the processor chips to shrink, unlike that one that I showed you that wasn't shrinking because of the SRAM. We believe that new architectures will reduce data movement inside the system, and we believe that cost performance improvements will continue. So with that, I'm ready to take questions, so thank you for listening. And I'm going to take advantage of the fact that we've got 2 microphones here. And I'm going to hand people the microphone too. So do you mind taking this from me? Thank you. Actually, I'm going to assign you the microphone one.
Okay, I can do that. So first question, I get first question then, right? So how does this change the ecosystem in terms of, there's new competencies here that align with old competencies or pre-existing competencies like fabrication, design, CAD tools. But particularly at the design level, does this create new opportunities for system builders, or at fabrication level, do the board builders get into this, or how do you see these lining up with the existing ecosystem?
I'm a hardware guy. You're a hardware guy. I don't see this as changing much of anything, because it used to be that you'd choose a DRAM chip, you'd choose a processor chip, you'd choose whatever you were using for I/O or whatever, and now it's going to go to, instead of building a PC board that has those different components on it, you're going to be building a complex of chiplets inside of a package that has those same functions on it. So it is going to go that way. Instead of using PC board design software, you're probably going to be using design software that helps you put together things on what's called a CoWoS substrate, or which means CoWoS is chip on wafer on silicon, and that's a TSMC proprietary substrate. Intel is planning on using glass substrates, but all of these very exotic materials, and that's going to take a little bit of a different kind of design CAD software, but that software already exists. So I think that it's all going to fall into place without there being any disruptions. I don't think that it will really take much time, because so many elements of it already exist. Okay, do you mind taking the microphone? And you can reassign the microphone duty to him if you want.
Well, thanks. Jim, I love your presentations with Tom. And for the last several years, you and Tom have been talking about new and old non-volatile memories. And I've been really excited about it, but I really haven't seen them making any progress into the industry and into fab. Can you name the 2 reasons that are holding it back?
Yeah. It's the thing that's holding new memories back is mostly economics. And it's anytime you make a semiconductor in small volume, it's wretchedly expensive. If somebody decided that they were going to make one chip, and they went and bought all the tools that they used to make the chip, even if they bought the minimum amount of tools, and because of that took a very long time to make the chip, they'd still end up having a chip that cost tens of millions of dollars to make. And that's a really expensive chip. So as you grow with the volume, if they made 10 chips, then it would probably cost about 1/10 as much, and you keep on doing that. DRAMs today sell in tens of billions of units. And in order to compete against DRAMs, you have to be near that level of volume to do it. Now, that said, if that works if you're making memory chips that are to compete against DRAM. But if you're making them for a different thing, then the economics are influenced by something else.
Suppose we're looking for the LED equipment of the incandescent bulb, a drop-in replacement for DRAM. Who's closest, both in terms of lithography equipment that can fabricate it and the opportunity?
All of the DRAM makers can make this, and so they all have programs going on, research and development programs, to try to, they're looking at MRAM and ferroelectric and, they've kind of stopped looking at PCM for a while, but resistive RAM. And they have contracts with a whole bunch of research firms for this kind of thing. So, that's going on. And Micron actually, I think it was December before last, showed off something that was a 32 gigabit DRAM, but not a DRAM. It was made with ferroelectric memory. And it was, they made it on the regular DRAM, pilot production line. And it was a non-volatile thing that looked like a DRAM. They decided, for whatever reason, they weren't going to follow through with that. And, I wouldn't be at all surprised to see that idea rise back up in the future, because DRAM is also stalling in its scaling. One in the back. And you're allowed to reassign the microphone to somebody, too.
Thank you.
There, run away from it.
You showed at least three other persistent memory technologies. Can you comment on the reliability or other metrics, right? Not just the power consumption. Power consumption looks great.
Yeah.
But what about the reliability metrics, data retention? Is there any view on that?
Yeah, I'd say probably all of these are far better than flash memory from a reliability standpoint. Flash, I know a guy who used to work on a flash production line for a long time. You probably know Mark Webb. And anytime you ask him about flash, he'll say, flash is shit, but somehow they make it work. Flash bits fail all over the place, but you've got error correction to take care of that. You've got other ways of managing that same kind of thing. This knowledge about how to do that is useful for these other memory technologies, but they don't seem to need so much of it as flash does. So and you can write in place. They all do have wear mechanisms, but the wear mechanisms seem not to be quite as bad as flashes. Now, DRAM has no wear mechanism. And so, that's a place where you're going to have a big advantage with DRAM that you have over flash. But now, with today's DRAM, you're starting to get into places where there's bit corruption happening for various reasons, mostly because of what's called disturb, which is when two bits close to each other, one of them gets written to, and all of a sudden the other one flips because, it kind of sympathetically it saw what was going on there, and it kind of followed suit. And that's kind of a noise issue. We've gotten into an area where DRAM has some reliability problems. These other memories will have those same problems, but I'm not expecting for them to have those problems any worse than DRAM. So they'll be worse than DRAM because they wear out, and that will have to be managed, but that is really understood well because of NAND flash. But they're better than NAND flash because of the fact that they don't have as much strangeness going on. Got 2-minute warning here. There's one more question. Why don't we make that the last question, if you don't mind?
Question on optical chiplets. So you've talked about logic and memory integration already happening with chiplets and seems to be making progress. What do you see as the biggest hurdles to get optical chiplets enabled with, say, logic or memory? Is it process? Is it substrate? Is it yield? Is it power?
There are people who are already doing the optical connections. I think that it just was a little bit slow to come online, but I don't see anything that's going to stand in the way. I think that probably the biggest thing is just that today optical is mostly used for great long distance connections. And you have to really get the data transmission rate up to a very high rate to make it worthwhile to get rid of a little short piece of copper, less than a meter piece of copper, and replace it with optical. And that hasn't happened yet. And so because of that, the fiber is used for chassis to chassis, sometimes for server to server or server to rack, or I'm sorry, top of rack network connection. But I think less often for that, because that's 1 meter, 2 meters at the most. So it's probably data rates that are going to really cause that to happen. I don't know. Should I take another question? Okay. Well, I want to thank you for being a great audience.